Thank you very much. It's a real pleasure to be here, and also a huge thanks to BITS and the Smart Grants funding for making this project possible and allowing Alexander Sahn to spend a tremendous amount of time working on this instead of teaching, which has been absolutely fantastic. As has come up multiple times this morning, there's a crisis with transparency and reproducibility. A lot of that work is focused on experimental research. There hasn't been as much on model specification, even though that's been a long-standing concern, even long before Ed's famous paper. Here, we're focusing on one aspect of model specification, which is hidden discretion in people's covariate choice. And everyone worries about this problem, but no one ever seems to do anything about it. And it's partly because it's a really hard problem. Nobody knows the true model. And also no one knows what covariates researchers could have used in most situations. Our approach to try to get at this hard problem involves a meta-analysis of the American Journal of Political Science, volumes 56 through 59, which is one of the leading journals in our discipline. And they adopted partway through volume 56 a strict policy of posting data and code. And we selected articles according to a pre-analysis plan. We can't go into all the details here, but just very briefly, we selected articles that focused on a key causal claim and had a statistical model in it with at least 3 covariates. So I'm just going to briefly show you the data, motivate our main test of whether or not researchers are, to some extent, exploiting hidden discretion and covariate choice, and then turn it over to Alexander, who's going to present the results. And also, if we have time, talk a little bit about the added uncertainty from specification that we see in these papers and recommendations. This is, of course, very preliminary, and we're eager to have and hear people's comments. 56 studies met our criteria in our pre-analysis plan in these volumes. Very much to our surprise, we were able to replicate all these studies with their code almost exactly. We have there on the y-axis the log of the coefficient of the key estimate in these papers, the estimate that got the paper published that we're focused on, against on the x-axis our replication coefficient. There's 1 or 2 that are just ever so slightly off the line, but very good to our surprise. That's the distribution of studies. We've got observational studies, experiments, natural experiments, and sorts. So how do we try to get a handle on this hard problem? Well, I think you're going to find our approach somewhat controversial, but I hope still interesting, partly because just no one's ever looked at this sort of thing before. Our key test statistic is to compare the key estimate that got the paper published from a minimal specification, which in many cases is just the bivariate, but it's whatever specification you need for that key estimate to make sense. If it's an interaction, that includes main effects. If it's an experiment with a lot of conditions, it includes indicators for the other conditions, fixed effects, etc., compared to the specification with all the covariates, what researchers usually present as the full model. And we're just going to look at what happens to the key estimate that got the paper published from a minimal specification, which researchers only showed at about 30% of the cases that we looked at. But we can now see, because we have their replication data, to a specification with all covariates. So why is this an interesting thing to look at? Well, it's because researchers have a tremendous amount of discretion in which covariates they include in their models. And all covariates can be classified as either deflators or inflators. They can have those effects for many complex reasons, but they all have those sorts of effects. And what we think should be going on in these papers is that people should be predominantly using covariates to deflate their estimate compared to this minimal specification. And why is that? Well, we just think that's good science. If you've got an effect, then you should be trying to put in covariates that capture alternative explanations that would make that effect go away. And of course, including variables that inflate your estimates that would capture suppressor variables can be very reasonable and justified. But there's a problem that because we don't know the true model, adding inflators does not debias. And adding more covariates doesn't necessarily debias on average. It doesn't get you anywhere closer to the truth unless you get the actual true model, which of course almost no one ever knows, has come up already a couple times during this talk. Yeah.
So you're speaking in terms of t-statistics, I guess, but maybe we want smaller standard error. So maybe thinking in terms of correlation versus standard error before meaning.
Yeah, so I think that that's right. And of course, there are many justifications for including covariates. The problem is that if you throw in covariates to soak up noise and reduce your standard errors, and they happen to be covariates that inflate your estimates, you're in dangerous territory. So think about the case, if I have a really nice, strong bivariate relationship, I've got a great I'm really worried about some omitted variable. I throw that in there. It makes my effect go away. And then I think, you know what? It'd be really great to soak up some noise in there. So I'll throw in this other variable that happens to inflate the estimate back from 0 back to what it originally was. I've just undone my attempt to eliminate this alternative explanation. And I think this is an uncomfortable fact that people don't think about nearly enough when they're doing this sort of observational work, but it's true. So we think that the best practice should be to be conservative and try to kill your result. And so that's one reason why we think that researchers should be deflating their estimates. Another reason to think that researchers should be deflating their estimates is that's what they tell us they're doing when we read these papers. That's what researchers say they're focusing on. In the 56 studies that we read, 68% justify inclusion of covariates on some sort of deflator-like ground. I'm trying to address an alternative explanation that could be producing this relationship. Not a single one explicitly justifies a covariate as some sort of inflator, but we do see about 32% only have a general soak-up noise type or include standard covariates measures. So, of course, there are lots of good reasons why people should be justifiably including inflators in their models. We think that puts them in very dangerous territory because they might be undoing any attempts to reduce confounding. You can imagine a route to publication is to say, no one else has been able to find the relationship between X and Y. That's because that everyone thinks should be there. We've finally uncovered some suppressor, and so now you should publish our paper because we've been able to find this relationship. None of our papers have that quality. We're currently going through them again, looking for cases that might have some strong negative selection process that would produce an inflation process. Certainly none of them overtly appear that way, although maybe more careful reading will be able to discover them. And it'd be interesting if you have other thoughts about mechanisms that would produce very strong inflation that would be justifiable that we could find even if researchers aren't explicitly justifying their papers on that ground. So, yeah.
Just for the maximal test statistic, so how many of these data sets
Yeah.
the full data set as opposed to just the replication data? So that shows you what their full degrees of freedom were.
Yeah, my sense is that most of them, and Alexander can probably do a better job answering that question, most of them just give you the replication variables. But that's something that we thought about doing, is trying to take advantage of the fact that sometimes they leave covariates in there that they didn't necessarily use. And so our expectation is that we should generally find covariates net deflating the key estimate relative to a minimal specification. Hacking, just publication bias, other processes like that should lead to either no net deflation or even inflation. And now I'll turn it over to Alexander.
Great. Thanks, Gabe. So we went through all these 56 papers and took their replicated results and compared that to the minimal specification, believing that we should, on average, see net deflation. And this plot here just shows our key test statistic, which is the percent change between the minimal and the full specification. And as you can see, very few of the papers deflate. On average, the mean inflation is 7%. The median is about 0, but we're seeing over 50% of the papers have an inflated result relative to the minimal specification, and that about a quarter of these inflate pretty significantly, more than 10%. So perhaps a more clear version of what we're trying to look at can be found in experimental studies. I think the question earlier gets at this, which is, normally in an experiment, because you have randomization, you don't have to control for confounders or correct a lot of selection. And you're just using covariates for covariate adjustment to improve precision, shrink standard errors. But because you're not changing the effect size at all, we shouldn't see a lot of inflation here. But in the 14 experimental studies that we looked at, we see there's about 5 of them that have a pretty significant inflation. The mean here is 5%, which is slightly lower than the sample as a whole. And there are just these outliers here that have large inflationary effects, and almost none of the experimental studies have a net deflation. Another thing that we looked at was to check the p-values. So obviously these studies are all published in one of the flagship journals of our discipline. It's very unlikely that their results would have been published with a p-value of greater than 0.05. But we looked at the p-values on the minimal specification that most often were not presented in the papers. And we found that about 38% of them have a minimal specification that is not statistically significant. And we were wondering why this is. So this again is just another plot of the percent inflation, and you see that all of these studies, the ones where the minimal specification was not significant, have large inflation, and none of them, or I think one of them, deflates. So the average inflation here is 27%. Remember, compare that to the 7% mean inflation for all studies, and we see the median inflation is also quite high. So we tried to look at whether these studies were either increasing the magnitude of their estimates or shrinking the standard errors. And we were hoping to see that people were using covariates to improve precision, not to change the size of their estimates. What we found, though, was that 80% of these see inflation, so the magnitude of the estimate increases, but less than half of them have a corresponding improvement in precision. So 47% of them have the standard errors shrink, which means that people are using these covariates, or the effect of these covariates is simply to increase the magnitude of the estimates, to move them further away from 0, and that drives the improvement in statistical significance. So we found that on average, the deflation that we expected to see largely doesn't exist. And we thought further about how researchers are using covariates and what the uncertainty associated with this is. And we tried to quantify that in a couple ways. So there's been a lot of proposals for this, and the one that we kind of used as a starting point was the specification curve from Simonson, Simmons, and Nelson, which is basically designed to estimate all plausible studies that one could have run given the data. And that's not really possible to do systematically in our meta-analysis, so we kind of limited the scope of the specification curve to control for all possible covariate combinations. So that is, given the set of covariates that researchers used in their full specification, to look at the results that they would have gotten had they used different combinations of covariates. So you can think of this as a generalization of just a standard practice, which is to present a regression table with 4 or 6 or 8 different specifications using differing numbers of covariates. And this is just a more systematic extension of that. And we're going to be calling this just our specification curve with the covariates. And we're also seeking to incorporate a couple different things with the specification curve. One is to bootstrap the specification curve to get an idea of how the particular set of covariates that researchers use interact with their particular data sample to possibly produce extreme results or false positives. And we're really open to suggestions on how to proceed here, and look forward to your feedback in the Q&A on that. So to give you an idea of how much uncertainty or leeway is associated with covariate choice, we tried to devise a measure of the uncertainty associated with specification. So what we did was we took the presented estimate, so the full specification, and just calculated a standard deviation of all the other possible covariate combinations around that full specification. And to put that into context, we just made a ratio of that standard deviation to the standard error on the key estimate presented in the paper. So this plot on the right here shows that ratio. So anything with a value greater than 1 has a standard deviation of the specification which is larger than the standard error on the key estimate in the paper. So 30% of these studies have this ratio over 1, where we're seeing a large degree of uncertainty associated with covariate choice. Yes?
So you're thinking that the standard deviation of beta hat for your different specifications is like the sampling distribution, and it should go to the standard error.
We're not saying that it should go to the standard error. We're just trying to see what the degree of uncertainty is relative to the standard error. And given that a lot of these papers, have a p-value of slightly under p, 0.05, the fact that there's even just a little bit of uncertainty associated with covariate choice might, cause us to rethink the finding, or just to be able to better quantify the error associated with the regression model.
Yeah. I don't know about anchoring this at 1, this ratio. I don't see a natural reason. You might want to do it just to scale the standard deviation. I just don't know if and then put it in units that are relative to the sort of sampling variation we have in our mind. But I don't know if I'd put so much emphasis on the ratio of 1, because I don't know what that means, that statistic.
Yeah, I agree.
So.
It's, there's no real threshold that we wanted to present, just to show you what the size of these uncertainties are. So another thing that we looked at was inspired by Ed Leamer, which is to look at the number of specifications that achieve statistical significance. So the kind of gold standard is to consider a result robust only if all possible specifications achieve statistical significance. So we tested this on the 56 papers that we replicated and found that only 30% of them achieve statistical significance across all different possible sets of covariates. And that's plotted here on the right, where the y-axis is simply the percent significant out of all possible models that we ran. So to wrap up, as Gabe said earlier, we would generally expect good scientists to be including covariates that deflate estimates. They should be trying to account for alternative explanations, soak up noise, and in the cases where they are including suppressor variables or covariates that inflate, these should be justified in the text of their papers. We don't see that in our reading of these papers, and if you do a Google Scholar search of suppressor variables or other phrases that would indicate that, it seems to be something that's relatively rare. And of course, that could just be due to the forces of publication bias, and reviewers don't want to see someone say, oh, I'm explicitly trying to inflate the size of my estimates. But in the interest of transparency, we think that that's something important to justify. Our finding is that covariates are only significantly deflating about a third of the time on average. And so the next time you crack open your issue of the American Journal of Political Science or another top quality journal which has a regression table in it, you should be looking at these covariates and not assuming net deflation. And to bring the uncertainty associated with covariate choice out into the open a little bit more, we think that readers, editors, and reviewers should just simply ask to see the minimal specification, that is, in most cases, the bivariate, alongside the full specification that the author has chosen. And in the cases where these estimates diverge, or whether the bivariate estimate is not statistically significant, we think that the researchers should have to explain their choice of their model and why they think that their particular method better captures the truth. And then finally, we think it would also be important to see the specification curve, not just the ones that we were able to run in our meta-analyses, which just look at the covariate choice given the set that the researchers used, but also full sets of possible covariates, different codings of the variables, and all of the different researcher degrees of freedoms that go into these studies. So thank you, and looking forward to your questions.
For those of you who don't know, I'm Ed Leamer, so this is a very exciting piece of work that you've done here, and I'm happy to have the opportunity to comment on it. First of all, you need to know I've been working on this in a way all my life, and I've been ignored completely, and so it's great to have this Leamer-Rosenthal prize as if I really exist. But having an impact on real practice is what we all need to be hoping for, and that's tough. My latest attempt is in the Journal of Econometrics, where I produce what I call S-values. And the S-values are supposed to go with T-values and P-values. The T-values and P-values measure the coefficient relative to zero in a statistical sense, whether we can believe in the sign. The S-values are perturbing the model where you have a large set of covariates, and it's an explicit discussion of how the range of perturbation which is allowed and the consequent implication of that perturbation for the coefficient in question. Now, in that paper, I said what you just said, which is you're obligated to report the simple correlations because that's really in the data. The partial correlations are something you cooked up by selecting the covariates. So that should be the kind of anchoring point of any statistical analysis. Now, I think you got to be careful in understanding that partial correlation is an answer potentially to a very different question than a simple correlation. The example that I really like is in these cross-section growth equations, where if you regress growth on per capita income, you get a positive coefficient, which says the rich get richer. But if you control for other variables like education per capita or land per capita, then that coefficient switches to a negative. Those are both features of the data. One model says positive, the other one says negative. How do we interpret the negative? The answer is that if you control for all the determinants of per capita GDP that economists normally would, then that GDP per capita variable is really a TFP variable because you controlled for the variability that can be accounted for by traditional measures. So the reason you got a negative coefficient, a positive coefficient when you control for the covariates is because there's technology transfer, that the low-income countries benefit from having a technology transfer. So what I'm trying to say is that both the simple correlation and the partial correlation have value in that setting. They help you understand what's really going on. And what I'm getting at is the need to have stories. It's not just patterns, but it's stories. I try to emphasize that in my classes, that this stuff really doesn't come alive until there's a story associated with it. And I try to illustrate that with the per capita income case. So I'm going to leave you with a puzzle, and it's related to stories. So the macro data is all set in stone. It's not like you're running another experiment. It's not a pooling problem. It's just digging out the appropriate covariates in every particular setting. So we can imagine two researchers, one a male, say, who runs 1,000 regressions and is transparent, reports them all, and then says, this is the one I want to believe. And then say a female who got the same regression but just picked it out and said, this is the one I want to run. Is there some difference in the outcome? They suggest the same equation. Is there some difference in the way that we should review those two outcomes? I'll leave that as a query.
I'm not sure if you're going to answer that or you're ready for another question.
We'll ponder.
It's an interesting question. All right, so I'm going to ask you a question from the opposite end of the spectrum. So now imagine you have a fully randomized experiment. And on your last slide, you say, report the specification curve. I don't see why not if you don't have a pre-registered pre-analysis plan. Sorry. But if you do have a pre-analysis plan, which you didn't mention, do you go with that, or do you feel some special obligation to, in addition, present the specification curve, even if your your hands are tied?
So I'd say generally with the experiments we looked at, people were very good about both showing just a simple difference in means, ATE, and then also a regression adjusted result. And generally, you know, if you're specifying a set of covariates to adjust by in your pre-analysis plan, it's great to show both that and the minimal specification and also the specification curve that leads, you know, that follows from those sets of covariates that you pre-specify. In terms of the ones that we looked at, I don't think any were early enough to have a pre-analysis plan, but it'll be interesting to see in the future how those types of studies, you know, show different types of results and different levels of robustness.
So I'm hoping that you drop that top bullet point, because I don't understand. I mean, the point of modeling is you want to present the correct model, and I agree that you should be transparent about how robust your finding is, but if there's something that's suppressing a result, then you'd want to report that. So, I mean, that just doesn't make any sense to me as a normative stance that we should try to report the smallest effects. But if you delete that top point, that would create some space at the bottom to add another really important point, which would be that just because you find a result is robust after including and excluding the variables that the researcher happened to collect does not mean that there's no confounding, right? So all that's saying is that the things they happen to measure don't capture whatever confounding might be driving that result. But just because you find that some result is robust across all of the specifications does not mean that you still should trust it. So that would be enough. You could fit that in at the bottom there.
I'm thinking of this crowdsourced analysis that Silberzan and Ullman ran with soccer players and skin color and referee calls, and how you got, you know, a bunch of different teams all doing very different analyses and getting, you know, sort of different outcomes. And I'm wondering, is that a practice that you think should be employed and displayed more often, or how does that exercise inform what you're doing right now?
Yeah, I don't actually. I think I've heard of that result, but what did they do with the crowdsourcing? They had people come up with various. Yeah. Oh, and work with it different ways. Yeah.
Then they had a bunch of teams write analysis plans all based on the same data to see if there was bias against skin color, and then they had teams critique each other's analysis plans and then run the plans, and it was sort of all over the map.
Yeah. If you haven't taken a look at it, I really like this Simonson, Simmons, and Nelson. Nelson is in the audience here, paper on this, which is something along those lines, which is the idea that you should lay out all plausible, reasonable models, and if crowdsourcing that helps you generate that set of possible models, that's all the better. And we would love to be able to do that for all 56 of these cases, but it'd probably just be too much work.
I have a question about your no covariate estimate ask. So if you're right about the problem that, you know, people are systematically using covariates to inflate, and if everybody kind of knows this, and if it affects both the credibility of individual papers and literatures as a whole, why wouldn't you make that journal policy as opposed to leaving it up to editors? So you could say, you know, like you and I run a journal, we say, if you have at least 3 variables and sort of, you know, your N is at least this, then a requirement is that you have this in there. So now it's public and you're satisfying everybody. So why is that a bad idea?
Sounds like a great idea to me. Yeah.
I'm just getting back to Don's point, which was, you know, in the case where you have a very clear sense of the right model, it's also Kevin's point, and I mean, Ed was getting at it too. If you have a really clear sense of what the right model is, and you've pre-specified what the right model is, and the right model isn't just the simple correlation between Y and X, that would be a case where I'd say, well, I mean, maybe in the appendix you could report that, or maybe when the data is available, you'd have it so people could look at it. But I may have a very good theoretical reason for saying I want to regress y on x1, x2, and x3, and I haven't data mined. I pre-specified it, and so that would be a reason why we might not want to tie our hands in that way.
Yeah, I think that's a good point. I think the one thing that I'd say on the pre-specification, which is of course a fantastic idea and really does tie people's hands, is that there's still you still have a distribution where by chance some people will pre-specify a bizarre model that just happens to give them a false positive, and so you still get some advantage from seeing the distribution across what might be other reasonable specifications. Yeah.